Hello, Phys Kids. Mr. C here, your physics teacher. And today we're going to go over the last lab of the semester, the 2D Momentum Lab. It's going to be very exciting, very cool, and very fun. Just to give you a setup of what we're going to be doing today. Our experiment will have two parts. Part one is we're going to look at 1D collisions. And the way this is going to be set up is we're going to use the exact same ramps that we use for our horizontal launch lab. The only difference is that instead of the ball just rolling off the ramp, it's going to collide with another ball at the end of the ramp. We're going to make this a head-on collision. And all this means is that all of our momentum is going to be in one direction. It's only going to be in the x direction in this case. And it will be a full transfer of momentum from ball 1 onto ball 2. Ball 2 will then go flying in this beautiful horizontal launch lab here, horizontal launch motion, until it lands a distance d away from our table. We are then going to measure the distance d from the table and use this information to calculate what the momentum of our ball is. Now that we have our lab set up, I'm going to go ahead and mark out where my plumb line down here meets the ground. The reason why this point is important is this is going to be the basis starting point for where we measure our distance. So we're going to measure our distance from here to wherever the ball lands, and that's kind of what we're going to record in our data table. As you can see on my ramp here, I'm going to drop the ball from the top of the ramp, and it's going to roll down the ramp and collide with the second ball, where all the momentum of the first ball is going to be transferred to the second ball, and then it's going to land here on this piece of carbon paper and mark where the landing spot is. I'm going to complete this 3 different trials for this. That way we can get a better guess as to what our actual distance is. And I'm going to make sure to drop the ball from the same height on the ramp each time. So for my first trial, I let it go, and it lands, and it hits the carbon paper. I'm going to move that over just a bit to make sure I hit it. I'm going to reset. We're going to launch again for our second trial. Perfect. And then finally, for our third and final trial, put it on one more time, drop the ball, and it lands again. I'm going to remove the carbon paper, and I see I have 3 landing spots all right around here. What I'm going to do in order to try and get the best measurement for the average distance is I'm going to draw a tight circle around each or all 3 of these points. And the center of that circle is where I'm going to measure my average distance from. So my average distance is going to go from this point on the plumb line to the center of that circle here. So if I put down my handy dandy meter stick, we go like this, I see that my average distance is right around 33.7 centimeters. So we're going to go back over to our data table, and we're going to record the distance to be 33.7 centimeters. I also need to make sure that I record whatever the height of my table is, because that's going to be important to know. So if I line up my meter stick here, and I read it off, the height of my launch is right at 75.3 centimeters. So my height will be 75.3 centimeters, and my distance will be 33.7 centimeters. Now that we've made our measurements and we know that our height is 75.3 centimeters and our average distance is 33.7 centimeters, we can use this information and along with the guiding steps in our lab guide to calculate out what our momentum was, what the momentum of the ball was after it leaves the ramp. And this is going to become very important because the momentum that we calculate here in step 1 is going to become our initial momentum that we use in step 2 whenever we do our error analysis. So it's very important that we are careful with our calculations here in step 1. Now that we've completed part 1 of the lab, we're going to go ahead and move on to part 2 of our lab, which is going to be 2D collisions. The only difference in our setup here is rather than having a head-on collision, we're actually going to angle ball 2 so that it hits at an angle. What this is going to do is after these balls collide, rather than both balls or ball 2 traveling straight, the ball 2 is going to travel to the right or left, and then ball 1 will travel in the opposite direction. And this means that our total final momentum is going to have both an x and a y component. For this case, we're going to measure our x and y component using our paper on the ground. And I'll draw out a little coordinate system there so you don't get confused. Whenever we talk about X and Y momentum in the case of this lab, we're not talking about up and down and left and right. We're actually just going to be looking on a top-down view of a piece of paper. So try not to get confused with that. For the purpose of this lab, we have to measure a few more things. We're going to measure the height, and it's actually going to be the exact same height as it was before because we're using the exact same ramp and the exact same setup. But we have to measure the distance that ball 1 travels, the distance ball 2 travels, but also the angle that ball 1 and 2 make with the horizontal, which we'll see on the graph paper whenever we get on there. So we need to measure both the average distance, but we also need to measure what the angle is that the ball makes, that our distance or displacement makes with the horizontal. Now that I have this all set up, I'm going to go ahead and run our experiment the exact same way, except now I have our ball here angled off to the side so that ball 1 is going to travel toward me, and ball 2 actually, because this is ball 2, is going to travel toward me, whereas ball 1 is going to travel away from me. Once again, I'm just going to drop the ball from our ramp. It's going to roll down the ramp, collide with the ball at the end, and then they're both going to fall onto the carbon paper. And I'm going to repeat this 3 times so I can get a good average. So I'm going to do this. 1. I'm going to reset the balls. Then 2. And then 3. So what I'm going to do now is the same sort of process before. So I'm going to remove that carbon paper. I'm going to do a tight circle around my dots. So that's ball 1. And that's going to be ball 2. I'm going to do the center of that circle, and I'm going to measure what my distances are. So if we measure the distance of ball 1, I see that the distance of ball 1, might have to move you guys for a second, is right at 18.7 centimeters. I'm going to draw a nice line there. And if we look at ball 2, and we measure that out, we see that ball 2 is right at about 27.9 centimeters. So that's ball 1 and 2. Our next step is we're going to measure our protractor. I have to go grab one real quick, so I'll meet you back here in a second. Now that I have my protractor, we can go ahead and measure the angle. So for ball 1, if we measure the angle, and we're going to measure it from the incident line, we see that ball 1 makes an angle of 46 degrees. Whenever we look at ball 2, we're going to measure that angle, and we see that it makes an angle of 23 degrees. Now that we have those angles recorded, we're going to go ahead and head on back over to our data table so that you can see it more clearly. Now that we're back, here is all of our data. So our height, once again, is going to be the same height as it was in trial 1, which was 75.3 centimeters. Our distance 1, or the distance that ball 1 traveled, is 18.7 centimeters, and the angle that it makes is 46 degrees. For ball 2, we traveled 27.9 centimeters, and our angle is 23 degrees. And our diagram is going to look something like this. So this is where each of those measurements lies. Using this information now, we want to find out what the final momentum of the ball is. Whenever we find out what the final momentum of the ball, using our calculations or a similar method of calculation that we used for part 1, is we're actually going to find out that that momentum points along this line here and this line here. And we can see that if we define our coordinate system, and we call this, say, the x-axis, and this here the y-axis, each of these momentum vectors, so momentum of ball 1 and momentum of ball 2, has both an x component and it will have a y component. Because all of our initial momentum is going in the x direction here, we can already go ahead and say that the momentum of ball 1 in the x direction, or the final momentum of ball 1 in the x direction, plus the momentum of ball 2 in the x direction, has to be equal to our initial momentum, which is the momentum that we calculated from part 1. If we look in the y direction, on the other hand, because initially we have no momentum in the y direction, we can go ahead and say that the momentum in the y direction for ball 1 plus the momentum in the y direction for ball 2 must be equal to 0. And we're going to want to check and see how close we are to these actual answers. So we're going to want to compute a percent error where we use this here as our actual value. And then the momentum that we got from part 1 is going to become our theoretical value. We're not going to quite do a percent error for this one because our theoretical value would be 0, and that would not give us any percent error. We would get some undefined number, which is not good. So all I want you to do for this one is I want you to compute a percent difference. So percent difference between the momentum of ball 1 in the y direction and the momentum of ball 2 in the y direction to see how different they are, because they should practically be 0. It should be the same number, honestly. But we're going to have a little bit of experimental error that's going to make that not so. The last thing you need to know for this lab, and I forgot to tell you for part 1, you will need this for part 1, is you need to know what the mass of the ball is. And in this case, the mass of ball 1 was equal to the mass of ball 2. And we know that that mass, which I'm going to write over here, the mass of the balls is equal to 8.4 grams. Remember, although we recorded all these numbers in grams and centimeters and such, you will have to convert them into meters and kilograms so that you can get accurate calculations. And that is all that I have for you on our last lab of the semester. Very exciting stuff. If you have any questions, please feel free to ask me, reach out to me. I'd be more than willing to help you, or reach out to OC if you have her as a teacher. We would both be more than happy to help you out. I will post pictures of our data on Canvas and send them to OC so she can post them on Canvas. And you can also find them on Instagram. I'll post them on my class Instagram page if you would rather look at them there, because sometimes it's a little bit easier to access. But that's all I have for you today. Thank you, and I hope you enjoyed this wonderful lab from Mr. C.